Hey y'all, I've got another example session with KVL and KCL. This time I'm going to try to explicitly use KVL and KCL as well as use one of each, and we're going to do some power calculations to verify our results. So let me go ahead and draw up a circuit. Okay, I've drawn us up a nice example circuit. I have elements A, B, C, and D, and I've labeled voltages and currents for each, some known, some unknown. So let me talk about those real quick. We have VA, which I've said is 10 volts, and IA, which is 2 amps. On VB, it's unknown, but and so is IB. Both VB and IB are unknown to start. VC is unknown, but we know IC is 1 amp. And on element D, we have that VD is 4 volts. I'm sorry, I know that's kind of smudged, but I have 4 volts here, and then 1 amp for ID. Now, before I say anything else, just think about what's going on here. Look at the way I've drawn certain polarities and certain reference currents, reference current directions, and what that might mean for how those voltages or currents are going to turn out, and whether or not you think these elements are sourcing or consuming power. Some of them you can tell automatically, some we're not sure yet. So just think about that as we go into this, and now let me introduce the question that I want to ask here. So I just want to identify the unknown voltages and currents, and then we'll look at the power in each element and verify that power is conserved in this circuit. So what is a good starting point? I think, well, some elements we have all the information and some we don't. But VC, we have at least half the information. We know it's current right away. So to gather the rest of the info, why don't we go ahead and figure out what VC is. And the first thing to notice is, like, you think, okay, our options are to try and do a KVL around this loop with ABC and figure that out. Or we can do a KVL around this loop with C and D and try and figure that out. The problem with ABC is we don't actually know VB. So doing a KVL analysis there won't actually tell us VC because we have 2 unknowns. But doing a KVL with C and D should work because there's only 2 elements in this loop and we know the voltage across the other element. And this is actually the trivial case of a parallel circuit. So we don't actually even have to write out any algebra for this. This should be very clear. So these 2 elements are in parallel, and they share the same polarity here, and they must because they're in parallel. And even if I had drawn the polarities the other way, you would then recognize that one of them is incorrect because they must have the same polarity, the exact same voltage, because they're in parallel. So given the fact that we know VD has 4 volts with this polarity, VC therefore must be 4 volts with the same polarity. So the initial drawings for these polarity markings are correct, and we know that VC is 4 volts. And that's fantastic. And so when you see a parallel circuit like this, again, what that really is, you know, it's a KVL. But it's just this trivial case where you don't actually have to write anything out. It should be clear instantly. The case of 2 elements in parallel is just as trivial as 2 elements in series. We actually know that 2 series elements have the same current. And that's actually a good segue because look over here at A and B. Here we actually see that we have A and B in series, and we know the current IA. Which means we actually automatically know the current IB. And kind of like I talked about in the last video, we have this case where the reference direction for B disagrees with A. So all that's going to tell us is that IB, according to this reference direction, is a negative current. So what I would write here is that IB equals negative 2 amps. But again, that's just with respect to this arrow. So really, it's just 2 amps. But it's pointing in the other direction. It agrees with the direction A, so it's flowing up and then to the right. And so if this arrow had been drawn the other way, I would just say that IB is 2 amps. Now, there's one piece of information we still don't have, and that's the voltage on VB. That's the voltage on B, VB. And in this case, now we are going to do a KVL because well, there's two ways we could solve this here, but I do want to step through an actual KVL because I feel like I haven't done one of these explicitly in an example yet. So if you recall, the way we set this up is we're going to pick a convention and start at a single node somewhere. So there's 3 nodes in this loop. We have the node connecting A and B, the node that connects B and C, and also D, but we're not concerned with that. We just care about this loop. So then this node, and then the node that connects A and C. And I'm going to say, in this case, that when I step, when we're stepping from this minus to a plus, that's maybe it's positive, right? And then if I step from this minus to this plus, that's a positive. And then when I step from a plus to a minus over element C, that will be the opposite polarity as the way I counted A and B. And what that means is I can just, kind of like with KCL, where I say, oh, the sum of current entering equals all the currents leaving. You know, whatever current enters a node must also leave the node. So it's equivalent to saying the sum of all currents entering is 0, or the sum of all leaving is 0, or the total entering is the total leaving. So just like we draw that kind of shortcut with KCL, the shortcut with KVL is to just say that, like, okay, all the way that you step up, so we step up, and then on this next one we're stepping down. So the sum of your step ups must equal the sums of your step down. So rather than writing out the explicit form of KVL where I just say, this plus this minus this plus this equals 0, I'm just going to kind of concatenate and write maybe a simpler or more clear algebraic form where I just have, something equals something. So you can see that what I'm going to do here is, I guess I'll write over here VA as we step up, that's a plus. And now we're going to step up again, plus VB. And now I'm stepping down and finishing my loop. So I'll just say that equals the total step down VC. And this would be equivalent to writing, VA plus VB minus VC equals 0. Right? That would be the explicit formulation of KVL, where I assign VC a negative because it's the opposite polarity with my agreed upon convention for summing voltages, and then I write that the sum equals 0 because that's the explicit form for KVL. But I'm just taking a shortcut here and saying all these steps up must equal all the steps down because energy is conserved in our circuit. So VA plus VB equals VC. Now let's take what knowledge we have and apply this. So we know that 10 volts, which is VA, plus the unknown VB equals 4 volts, which is VC. And then if you solve that quick algebra, VB, therefore, equals minus 6 volts. And you might be thinking, what? Well, no big deal at all. I know I haven't shown an example where this is the case yet, but this is just like it's the exact same issue as IB and IA here, where we know the direction that IB is actually flowing and that it disagrees with this arrow. So we just assign this negative to it. And what we've revealed here is that VB is 6 volts, but the minus indicates that its true polarity is actually the opposite of the way it's drawn in this circuit. So in reality, the polarity of element B has a plus on the left here and a minus on the right. And so as the circuit is drawn, this minus just captures that. This saying the voltage is minus 6 means that the true polarity is the opposite of this. So we could redraw the circuit with the correct polarities for all the voltages and change the directions of the currents so that every value could be positive. And that's equal. That's the same thing. And you could do that, but it's just extra work. I don't need to redraw this circuit and correct things. I can just capture that with giving a negative current here and giving a negative voltage here. So there really isn't such a thing as a negative current or a negative voltage. This is all just polarities and references, and it's just convention. So these are physical phenomena that are happening. And now we've actually accounted for all the voltages and currents. And because we have the voltage and current for each element, we have complete information about it as far as calculating its power goes. So, and again, this is interesting. We don't need to know whether or not these are resistors or some other circuit element, or what their resistance might be, for example. But we're just going to say that, you know, some of these are source elements and some of these are passive elements based on what we calculate here. And we're going to go through, find the power for each element and verify that it's conserved in the circuit. So the first thing is, let's find the power in element A. And when you look at element A, you go, okay, it has this voltage polarity and this current direction. And I'm saying they're both positive. So it's 10 volts with respect to this polarity and 2 amps with respect to this current direction. And the thing, remember, the thing to keep track of when identifying whether or not a circuit element is sourcing or consuming power is look at the current reference relative to the voltage reference. So in the case that the current leaves the positive node or the positive terminal of an element, that element is sourcing power. So if you see the current leaving the positive node, entering the minus node, that's a source. And at the same time, if you see the current entering the positive node, that's passive. Okay, so again, if you're leaving the positive node or entering the minus node, those are equivalent to, say, leaving positive or entering minus, that's a source. And if you see it entering positive or leaving minus, that's passive. And that just all has to do with our convention for voltage and current reference polarities and our convention for counting power, because we want it to turn out that passive elements have positive power, so a positive consumption in our calculations. Then it'll turn out that sources have negative power relative to our calculations. So let me go through and step through the power calculation for each element. Okay, so for element A, we have 10 volts and 2 amps with a current leaving the positive node here. So this is a source. And we have that because P equals IV, we know that the product of the voltage and the current in this element is the power. So A must have minus 20 watts, which reveals this is a source and it's sourcing 20 watts. Now if we look at element B, we have that there's a current here, and now this is really interesting. In our analysis, we revealed that the current B is actually pointing the other way, and that the voltage has the opposite polarity of what's drawn here. So I'm not going to redraw this, but you can just imagine that there's really a plus here and a minus here, and the current is entering this way from left to right. So in reality, what's happening is the current is entering the positive terminal of element B. And that's actually something that you can visually already see, because the way that's drawn on the circuit is to the left, and the plus terminal is right here. And this all works out because they're actually both negative. So you have -2 and -6, and that will manifest itself with the correct answer, which is that this is a passive element and the current is entering the positive terminal. This is consuming power. So B, as you can see, has 2 amps and 6 volts, or -2 and -6, either way you get the same thing. You have 12 watts consumed in this element. Now element C, we have a positive voltage and positive current that agree in reference, 4 volts and 1 amp. So there are, and again, current entering the positive terminal. So we have 4 watts consumed in element C. And lastly, element D, which must have the same voltage as element C, which we already know, and it also has 1 amp entering the positive terminal. So again, there's another 4 watts consumed in element D. And this is fantastic because if you add these together, you get 20 watts, which is a net power consumption of 20 watts, showing that we've conserved the net power generation of 20 watts from element A, which turns out to be the only source in this circuit, whereas elements B, C, and D are all passively consuming power. And so this is a really good sign that according to our calculations, power is conserved. And this is the type of thing that gives you confidence that you probably solved the problem correctly. Just because all this works out in the end, this isn't proof that you solved it correctly, but you probably did, right? It's possible for you to make mistakes and then things still work out in this respect. But again, this should boost your confidence a lot that you did the right thing. But what you should look for here is if these didn't agree, you would know for sure that you made a mistake. So just be aware that that's a tool that you have. With that in mind, I think that was a good example circuit. Again, I think I'm going to cut the video here. In the next video, I think I'll continue on this path. Maybe I'll get a little bit more complicated, and I'll see if I can introduce an example where there's a perspective or a scenario that I haven't discussed yet, just so we can start covering this topic a little bit more fully and really covering all our bases so there's no surprises or crazy questions that you might have. I hope this was helpful. Let me know if there's anything I can do to improve these videos, and thanks for watching, and have a great day.